Now we're up to the enolase reaction, which is a simple dehydration, and we form a double bond here with release of water. And finally, we have pyruvate kinase, which is again add a phosphate to pyruvate. So this is named for the reverse reaction. This is our second ATP forming step. So our second ATP has been formed. Now, the form of pyruvate that comes off of pyruvate kinase is not the keto form. So this is the keto form. We actually have the enol form that is released. And of course, this ATP is generated by substrate level phosphorylation. Here is the enol form of pyruvate that is released from pyruvate kinase. And then we have this non-enzymatic tautomerization in solution after this is released off the enzyme, and we end up with the keto form. Now, the keto form is inherently more thermodynamically stable because we don't have an enol present. So enols are notoriously unstable. Here's the structure of nicotinamide adenine dinucleotide. Know this structure. Again, I can't test you on this, right, because you're remote, but please memorize this structure. I promise it will make your life easier in the future. So we have nicotinamide adenine dinucleotide, and di means two, and nucleotide means that we have a sugar plus a phosphate plus a nitrogenous base. So these three things equal a nucleotide. Let's look at our structure here. Dun, 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 dun. Here is our first nucleotide. What do we have? We have the ribose sugar, the phosphate, and the nitrogenous base, which is nicotinamide. Down here, we have the second nucleotide, and this would be adenosine, right? So we have the sugar, the phosphate, and the adenine base. Before we go any further, let's clear up the last bit, and let's address what is NADP, right? So it tells you here NADP. So nicotinamide adenine dinucleotide, the P is for phosphate. And in NADP, we would have a phosphate group here. Okay, there's your NADP, but we are looking at NAD. It doesn't matter whether it's NAD or NADP, right, as far as the chemistry, the redox chemistry, because the redox chemistry happens here, right, at this carbon. This carbon can pick up a hydrogen and it can lose a hydrogen, along with the addition of the hydrogen. And it's showing you, right, two hydrogens go in, or two protons go in, and two electrons go into this situation. Here we have one proton plus two electrons, which are going to be covalently coupled to this carbon. And then we have one of those protons released to solution. So that's why you see the 2H plus and the 2E minus. That's where they're going. So we have this big molecule, this big, huge molecule, and we're really only doing business at this carbon here, where we add a hydrogen and two electrons, or we, can lose a hydrogen and two electrons if we run this in the opposite direction. When this hydrogen is added, it can be added either to the C face or the Re face. So maybe this is, making some bells ring for you from organic chemistry as far as stereochemistry of reactions, adding to the front face or the back face of a plane. Enzymes are very particular about their stereochemistry. At any rate, when we have addition of a hydrogen to this carbon, we're going to have a rearrangement of the electrons in the ring. So remember, this nitrogen has a positive charge. So this is an electrophile. This nitrogen is drawing electrons towards it, and it facilitates the addition of a hydrogen at this location in the ring. So remember, this is the para position of the ring. Okay, this is our benzenoid form of the nicotinamide ring, where we have a positive charge here on this nitrogen, and this is the quinoid form. So the reason that I'm presenting this NAD structure to you, and you should always put NAD plus, right? The reason that I'm presenting this to you now is because NAD plus is a cofactor for glyceraldehyde 3-phosphate dehydrogenase. So let's look at the mechanism of glyceraldehyde 3-phosphate dehydrogenase. And here we're going to look at this learning objective, apply the principle of high energy linkages to capture of usable energy. Use the thioester linkage as an example. So we are going to be forming here a thioester linkage in the process of catalysis. Here are our starting materials, and because this is an enzymatic reaction, instead of calling these reactants, we're going to call them substrates because we have an enzyme we're going to call them substrates because this is an enzymatic reaction here. NAD plus is a cofactor, and this is in solution. This is required to act as a hydrogen acceptor, and we're going to go from the benzenoid form of the nicotinamide ring to the quinoid form. And in the quinoid form, we have a free pair of electrons on our nitrogen. Something super important I want to impress on you, because it's implied in the way that the structure is drawn, but I want to make it super obvious to you. There is a hydrogen here, and we're going to add a second hydrogen. So even though it's not shown, there is a hydrogen there. Because this nitrogen is maintaining 4 covalent linkages, that nitrogen atom has a positive charge, and it's quite unhappy, and it would love to go back to having its lone pair of electrons, right, as you see here. Going on, let's look at the reaction mechanism for glyceraldehyde 3-phosphate dehydrogenase. In our active site, we have a deprotonated cysteine amino acid. This is unusual. Usually, the cysteine would be protonated because cysteine has a pKa of 8. And so it would usually be protonated at pH 7, like the majority of it would be protonated at pH 7. However, because of this specialized microenvironment, the specialized chemical microenvironment at the active site, we have cysteine in a deprotonated form. And guess what? That means that this sulfide is a good nucleophile. And so in the first step of our reaction, we have nucleophilic attack at carbon 1 of this glyceraldehyde 3-phosphate in order to form a thiohemiacetal. It's just like an acetal, but instead of having a group which would be, here's your thiohemiacetal. Instead of having a group that would have an oxygen here, and then this would be, right, the rest of the molecule, we have a sulfur, and then the rest of the molecule. This is a tetrahedral intermediate. We've gone here from sp2 hybridization on that carbon to an sp3 hybridization. So we have a tetrahedral intermediate. And when this tetrahedral intermediate collapses, we're able then to provide a hydrogen to NAD+. So we have this hydride transfer to NAD+, and we form a covalent enzyme intermediate. So we're making use of this concept of covalent enzymatic catalysis. So we're constraining that enzymatic intermediate to the enzyme active site so it doesn't diffuse away and we have to kind of have it re-come back onto the enzyme. This covalent enzyme intermediate has a high energy thioester linkage. And this high energy thioester linkage will be cleaved in the next step. The cleavage of this bond provides the release of energy to drive this next step forward. Here we have the release of NADH into solution, and we have the entry of a fresh NAD plus molecule. So it's not the same one, right? We have an NAD plus come onto the enzyme, and then we have the joining of inorganic phosphate, as you see here. We will have nucleophilic attack onto the carbonyl carbon and subsequent cleavage of this carbon-sulfur bond. So in this substitution reaction, we have the coupling of the phosphate at carbon 1, right? So this is also an example of phosphorylysis, using phosphate in order to split or break a bond. In our product, we have a phosphoanhydride bond, which is still considered to be a high energy bond. In the last step here, we will have diffusion away of the 1,3-BPG product from the active site, leaving our enzyme in its original state.